Warm welcome to all the dignitaries who have joined in today for the 10 hours faculty development program on quantum computing, starting today, 16th Feb at 3 p.m. And for the next 5 days, you would have the session from 3 p.m. to 5 p.m. So before we could get into the session, let me give you a quick walkthrough about XLR. XLR 2000, founded in 2013, having its branches in 5 cities, founded by IIM ISB alumni, headquartered in USA, Houston, having trained so far students and professionals close to 8 lakh plus. So we cater to the skilling needs of individuals, institutions, and industries. What sets us apart is our premium associations like iHub Divya Sampat, SkillUp, APSSDC, AppShe, TASK, KMDC, IIT Madras Pravartak, IIT Roorkee, BITS Pilani, Hyderabad, NASSCOM Future Skill Prime, Swayam Plus, BFSI, and ESSCI. We also have our courses on the NASSCOM Future Skill Prime and Swayam Plus. So through a decade of training excellence, we have so far trained faculties close to 80,000 plus and students close to 8 lakh plus, conducted strongly webinars, seminars, workshops close to 1,000 plus on the technical training programs 30 plus, and we have strong association close to 2,000 plus academy partners, and we have 5,000 plus placement partners. So through our everyday learning program, we have trained close to 8 lakh plus students under engineering, degree, and other category. And similarly, faculties from engineering and degree close to 70,000 plus. So for today's program, we have faculties from Pan India who are from regions like Andhra Pradesh, Telangana, Karnataka, Maharashtra, Tamil Nadu, Uttar Pradesh, standing very high. So we have close to 1,138 registrations for this program. So for today's everyday learning program, that is through everyday learning program, we support the students and faculties through complete industry-oriented learning with hands-on training on the trending technologies. And these training programs also support the colleges in fulfilling a few of NAC and NBA requirements, for which a learner has to register in the registration link, which is given here. And towards the completion of the program, the learner will get the participation certificate. For receiving or having bagging on the certificate, the participant should regularly attend all the sessions, mark the attendance, and the feedback must be shared so that he will be tracked, and there would be the certificate, which will be participation certificate, which will be issued to him. So through our everyday learning program, we conduct industry webinars. We sign MOUs with the college where the colleges collaborate with us for our everyday learning program. We strongly do a lot of professional training, industry faculty development programs, and all of this is done on the learning management system tool. We do a lot of industry use cases for the students on a real time with industry experts, and we provide the placement preparation platforms also through our LMS for the students. So that's how our LMS will look like, wherein the learner will be able to experience the upcoming events and the past events, that is the training programs which has already happened at XLR. So far through our journey, we have largely conducted close to 60 plus student development programs. Enrolled students for this program is close to 8 lakh plus, and constantly participating colleges are 2,000 plus. And we have trained the students on DSA, ChatGPT, Advanced Excel, Salesforce, Python, artificial intelligence, mobile app development, and various other category of programs. So the listed programs are the most popular programs, which is on repeat from the colleges and students, where we are training the students from the colleges. Similarly, we have faculty development programs so far conducted 45 plus. Constantly participating colleges are 1,590. Total number of enrolled faculties so far it is 80,000 plus. Similarly, here we see the most popular programs under faculty development program like AI, Gen AI, deep learning, artificial intelligence, digital marketing, data analytics using Power BI, Tableau, cybersecurity, NLP and ChatGPT, and various others. These are some of the most popular programs under the faculty development programs. So as I told you earlier, these are the certificates, that is participation certificate a learner will receive towards the end of the program, for which the learner has to regularly attend the sessions which is being delivered here, mark the attendance to receive the certificate. Here are some of the certificates which we had shared with the students and faculties for the training program in the past. And our recent engagements where we would want, which strongly speaks about our trust, is that training program which we have delivered at IIT Roorkee on data analytics using Minitab. Similarly, for students on Power BI at BITS Pilani, Hyderabad, this is a CSR initiative of XLR to train the students, final year engineering students, on to support them on cracking job interviews. So it was a 5 subject module, campus recruitment training with placement assistance, with complete 240 plus hours of training program, which had coding skills, quantitative aptitude, logical reasoning, verbal ability, soft skills, resume and LinkedIn profile building, tips and techniques to ace the job interviews through group discussion and personal interviews. And this was jointly in association with iHub Divya Sampark, where iHub Divya Sampark honored the students with the prestigious certificate from iHub Divya Sampark, joint body of IIT Roorkee and Government of India, Department of Science and Technology, where we had close to 50,000 plus participants attending this program. And the students who cleared successfully were honored with this certificate. We had received maximum participation from Andhra Pradesh through APSSDC. These are some of our past events under our everyday learning, where we have conducted student development program and faculty development program. So without much further ado, let me quickly get into our today's faculty development program on quantum computing. And it gives me immense pleasure to honor our dignitaries who have joined in today for this afternoon. I would request Dr. Mohan B. Vanaroti, Director of KIT COEK, Kids College of Engineering, Kolhapur, who has 21 plus years across teaching, research, and industry with a strong record of performance in diverse academy environments, and also has expertise in NAC and NBA accreditation, playing a key role in securing an A plus grade for the current institution, reflecting commitment to quality excellence. He has also proven research leadership, having worked on funded projects exceeding close to or more than 10 plus crores, supported by agencies such as DAE, DST, AICTE. A warm welcome to you, sir.
Thank you, ma'am. Thank you very much.
So, on behalf of Dr. Mohan B. Vanroti, I do have Dr. Lingaraj Adimani, Professor in HOD, Computer Science and Engineering, who would be sharing a few words. Sir, over to you.
Yeah, thank you, ma'am. Good afternoon, everyone. I hope I'm audible to you. First of all, my sincere thanks and gratitude to our director, Dr. Mohan Vanroti, sir, who allowed us to collaborate with XLR for this 10 hours FDP program on quantum computing. Secondly, I would like to thank XLR for this great opportunity. This is the second time we are collaborating with XLR. Last month, we had collaborated for one student development program, and I'm really thankful and grateful to the whole team of XLR providing one more opportunity for us. So this FDP is on quantum computing. It's no more a buzzword now because it's slowly you can see many quantum computing applications are taking over the traditional computing. Basically, it uses. I mean, it's quantum computing. This approach is based on quantum physics, where information is stored in qubits. Earlier in traditional computing, we use only two bits, zero or either zero or one. But in case of quantum computing, there is a third type of, like you can say, qubits, where you can save both these things parallelly. I mean, at the same time, you can store the information with zeros and ones. So that's what is the greatest advantage of quantum computing. Quantum computing is very powerful compared to traditional computing. For example, a recent study by Peter Shor, which has demonstrated that quantum computing can break the current encryption technologies that are being adapted in cryptography. So I mean, it's very powerful. And for example, if you want any drug companies, if they want to develop any new kind of drug, so they take 10-15 years earlier days. But with the advent of quantum computing, they can just simulation. They can use that molecular simulation and to produce a new sort of drugs. Basically, IBM and Google are using quantum computing technologies for this work. Then it can really solve complex optimization problems such as traffic routing or supply chains or portfolio optimization, airline scheduling. Such kind of complex things can be easily I mean, solved using quantum computing technologies. Even quantum computing can accelerate AI, which can really help us to create new materials, batteries, and even we can model the climate. So I mean, there are many applications of quantum computing. So I request all the faculty members to make use of these 10 hours to understand the basics as well as advanced concepts of quantum computing. I wish all the faculty members all the best. And once again, I would like to end with thanking once again XLR for this opportunity. Thank you, everyone. Happy learning.
Thank you very much for your kind words, sir. So let me call upon our next dignitary, Dr. Soumya PT, Professor and Head, Computer Science and Engineering, City Engineering College. So, Dr. Soumya, Executive Officer at City Engineering College, Bangalore, having 18 plus years of experience, holds a PhD from VTU, and she has published 30 plus conference papers, 29 journal articles, authored 7 books, and holds 7 international patents. She is a member of ISTE, IEE, IEI, IEEE, and IAENG. Her research focuses on AI, ML, IoT, big data, and wireless sensor networks. She guides 5 PhD scholars and has received Young Academician Award and Best Women Faculty Award. A warm welcome to you, ma'am. Ma'am, could you please share a few words? Prishmita, could you please check if you have given the access to Dr. Soumya to speak?
Hello?
Yes, ma'am.
Yeah. Now I've got the access. Thank you. Good afternoon to one and all present here. Thank you, XLR, for giving me an opportunity. Thank you, Dr. Mohan sir, for collaborating with the City Engineering College. Uh, XLR has been a great foundation for all the students in training them in various domains. So today we have an FDP and discussing on the topic on quantum computing. As Dr. Lingraju sir said, he was mentioning about some of the applications pertaining to cryptography. I would also like to quote here that quantum computing It is an emerging technology because even from the government of India, there are a lot of fundings being allocated through National Quantum Mission, which approved in 2023 with a budget of 6 lakh crore, and it is taken care by an Department of Science and Technology. So the main mission is to develop intermediate scale quantum computers close to 50 to 1000 qubits, which can enhance the secure communication, and it can also establish in India as a global leader in quantum technologies. So that is one of the area where government is trying to work on, as the quantum computing is not just enhanced towards cryptography, but also artificial intelligence and machine learning, and as well scientific research. It mainly has few applications, like it also includes simulating atoms in the drug discovery and material science. It also deals with financial modeling and risk analysis. It also deals with supply chain management and traffic optimization across networks, then artificial intelligence and machine learning acceleration. So now we have some of the fields like physics, chemistry, and maths, which can help us solve complex problems, numbers, and material science, which also deals with mostly engineering fields like electronics and electrical engineering, computer engineering, which deals with quantum algorithms, and also sometimes with aerospace for optimization problem. So in short, I would like to say quantum computers are super fast problem solvers. They are very much useful for the fields like cryptography, AI, and scientific research. So with this, I would like to just highlight a few things on quantum computing, and I would wish everyone all the best. Thank you. Thank you for giving me an opportunity. Thank you.
Thank you very much, ma'am, for sharing those kind words. Next, let me call upon our subject matter expert, Dr. Vipul Saxena, material scientist. He is a material scientist with 9+ years in quantum technologies, advanced materials, client consulting, plus 8 years of experience teaching quantum computing and AI. He is a key contributor to graphene-based quantum devices, photonic qubit interfaces, and semiconductor materials for the next generation quantum hardware. His proven ability in project management, research, global technical education across industry, academia, and professional platforms. A warm welcome to you, Mr. Dr. Vipul Saxena.
Thanks for introducing me. So good morning, good afternoon to all the respected dignitaries, colleagues, and fellow educators. It's a truly privilege to be part of this faculty development program provided by the XLR. Whenever I'm invited to speak at an FDP, I don't see it just another academic gathering. I see it as a space where the future of the education is quietly being redesigned or refurbished. So it is always a very special moment when educators gathers and accumulates not to only teach. It's a gathering that they are gathering to learn something, right? So, in my experience, some of the most important academic conversations do not happen inside the classroom. In fact, I had been associated in the teachings in last 10 to 12 years, either directly or indirectly. But these type of conversations, which we demands, which happens in the space like this gathering, where the faculty take a pause, take a reflection of these questions, and speakers ask a deeper questions like, so are we still preparing the students for the world they are entering? Because it's a 21st century is going to be end, and uh, there are era of AI and all this AI, ML, and machine learning. So what I feel over the last 15 years, working both with the academics and the closely with the industries, I had been an academician also. Now I'm in industry and corporate sector. But I have observed quite, but a powerful, a very powerful, I should say, a shift. The shift is this that this world outside our campus is evolving exponentially to all the faculties. But education, as you know, by designing the curriculums and all that, it evolves very gradually. So means the curriculum, what we are going to teach, we are getting from the universities and all that, that is evolving at very, very slow speed. So this gap between the exponential change of this era and the graduation adaptation is where this faculty development programs becomes very crucial. So let me begin with a question that if at the beginning of the day tomorrow, every student in our universities had access to perfect AI tutors and unlimited online course, as you know, everybody is there are free online courses and YouTube channels and all that, and real time knowledge from all over the world. So they are gathering now. So this is reality. So would they still require us? So this question bothers us. That question isn't born out of fear. It's about being clear. So I think because if technology can provide the information better than us, then our worth must be somewhere deeper. And that is exactly why these faculty development programs are important. So all these programs should always aims to be like that. And I found XLR is very good in this type of bridging the gap. So certain a long time ago, around 8 or 9 years ago, when I was just starting to teach, I was under the impression that the mastery of the subject was sufficient. If I am a master of the subject, I'm just used to lesson plan of my lectures before the day. And I was under the impression this that if I am mastering this, then it will be sufficient. So at that time, at 10 years or 11 years or more, that time it was very sufficient. Even though there was a use of internet and all that, the student used to search the number of questions in a Google and try to ask here. But that was also sufficient if you have a mastery. But later I got a chance to work with industry teams that were tackling real world problems, out of the campus problems, deadlines, market pressure. So lot of complexities are there. There are certain uncertainties in the work. So something we are going to complete the deadline or not. In the teaching, easily we can complete the deadlines. Even we can do it by the extra classes, right? But in the corporate sector, the marketing pressure was very much large. The complexities of these, uh, all the points, endpoints are very uncertain. So I had to face a humbling realization that a student did not find it hard because they did not have the right formulas. They found it hard because they did not have a right judgment. So this is my experience. It may be right or wrong. So and the judgment I think cannot be downloaded. In the IT language, I can say it cannot be downloaded. Right? It has to be grown within itself. So that was the turning point of my teaching perspective. And that is what a faculty development programs means, I think. So this is not a student problem, it's an ecosystem problem. So this type of program exists to strengthen the ecosystem. I will say it should not be merely a content update session in the faculty program. Rather than a content update session, it would be a judgment, refinement, and the development process. So this is all So most people's what I observed that most people think in the FDP it is about skill enhancement. Yeah, in some percentage it will be about skill enhancement, and in the long time ago it is only about the skill enhancement. But now the definition, I think we have to change the definition for that. So I would argue that there are about assumption disruptions. So every faculty member carries, yeah, hidden or invisible assumptions within themselves that what is important to teach is and what a student needs. So there are industry values and what counts as a success. So this all these criteria, but nevertheless what I also think that uh, the half-life of the knowledge, just like a half-life of any radioactive substance, the half-life of the knowledge is getting shorter and shorter. So what we teach today might be old and fashioned in the 5 years. So therefore, the point should not be, are we finishing the syllabus? No. It should be, are we preparing a students to solve problems that are not yet known? A meaningful faculty development program causes, I think, the intellectual discomfort. So intellectual discomfort means if you are feeling that it's very easily getting absorbed in you, then it will be not causing a stress to you. So if there is intellectual discomfort, if it is hard to understand to you, then this discomfort is the first signal that growth is about to begin. So it serves expert to transform into learner again. And when teacher keeps on learning, our campuses, our university, and stay vibrant. So as this FDP program deals with the emerging technology, I think. So in a quantum mechanics, a system is in superposition, a several possibilities until it is observed. So education is the same way. The students are in the superposition nowadays. When they come to our classroom, they are full of possibilities. We have to find out. So the teacher's role is not to decide on a narrow outcome for the students. It is to increase the extent of their potential and that pressurize us to continuously renovate ourselves. So we are entering an era where intelligence is no longer uniquely human now. So as I said, AI can write the reports. The AI can write the algorithms also, and it can detect the patterns. So the quantum system also challenges the classical logics. So what becomes the means I mean to say what becomes the role of higher education nowadays? So it is no longer an information transfer. It is a context creation, critical thinking, and I would say rather ethical type of reasoning, interdisciplinary integration. So earlier knowledge was scarce, now the wisdom is scarce, I should say. So the emerging technology is not just tools, they are the stress test for our education model. So they force us to revive ourselves, to rethink that how we design the curriculum, how we evaluate the students, and how we mentor the researchers, right? So with this, I hope that this FDP will help understand and to help to grow on the thinking in the same way what I thinking. So let's have a positive 5 days for that learning. So I'm handing over to uh, LMS portal training, and after that we will begin the session with the quantum computing. So hand it over to you, Nitya.
Thank you very much, Dr. Vipul Saxena. So now let me hand over the session to Mr. Amar Shivate, who will give you a complete LMS walkthrough, after which the session will be handed over to the expert. Over to you, Amar.
Very good afternoon to all the faculty members. So I will just take a 5 to 7 minutes of your time and I will walk you through the LMS portal. So once day one, all these things are ready. So from tomorrow onwards, you can utilize the LMS portal to join the session. You want to access the recordings and access the material as well. And not only for now, but similarly, you can utilize the same thing in the future as well. So again, if you want to go through the content or if it's stuck anywhere, so definitely you can go through the content again in the future as well, as you are going to have the access to around 1 year for this content. Okay. So let me share my screen. So first of all, as everybody know, LMS is known as Learning Management System, and how to access the portal. So to access that, as registration is important. I hope everybody is done with the registration. If anybody is pending and not received the LMS details, so our team will share the registration link in the chat box here over the Zoom and YouTube as well. So please, if you're not registered, if you not received the LMS access, complete your registration. Immediately you will also get the LMS access. So how to check that you received the LMS access or not, or what are the steps we have to follow to access the LMS portal? So the first thing, that is LMS portal account details by Excel. This mail you have to check. So while checking the email, you have to uh, check into the inbox sometime as it's bulk mailing from the automation system. So make sure that you are checking into the spam folder as well. And if you not received that, or if you attended any previous program, then you receive only welcome email. You will be not able to find the portal details. So I will give you the context on that as well, how you can access the LMS portal. Okay. So portal link, email address, password. So by using these details, you have to do a sign in. And second email, you will find welcome to the FDP on quantum computing by XLR. Okay. So this is just a confirmation mail that yes, so you have access for this classroom on the XLR LMS portal. Okay. So now I have my details. I have to do sign in. So what next? How I can follow that? So I have to click on this link. Okay. So let me reshare my screen and we'll follow the last steps, how the sign-in page looks like and how we can proceed with providing the details. Okay. So once I click on that link, mylearning.xlr.com login page, it will take me here on this page and I have to provide my details. Okay. So email address, that is nothing but your username and system generated password. If you check the email, so system generated password is a little bit lengthy. So in that scenario, you can just update the password after first sign in. I will explain that on as well. So couple of faculty are attended previous FDP or SDPs as well, and they already have the account details, but now they not receive the email. Definitely couple of you already receive only welcome email. But if we are not remembering the password, then you can utilize the forgot your password option. Okay. Update your password and you can access the LMS portal. So suppose I provided my details, I will click on a sign in. Okay. And once I click on a sign in, it will take me to the dashboard. And you can check here. Now, here I have option of back to homepage, community, leaderboard, dashboard, purchase history, health, and to the top of right corner, I have profile option. Okay. So clicking on a profile, clicking on settings, you can update your entire profile. But while updating the profile information, the most important thing, as I said, that you can update the password from the portal itself, right? So you have option here to update the password. Update the password again and confirm new password here. Both passwords are going to match, then update password button will be enabled. Okay, so this is how we can update the password. Then back to homepage, community, leaderboard, or purchase your help. So these are the things currently we not required, but the dashboard, which is something important part, so where we can access the everything. Okay, so the first thing, live session for today. So if you want to join the session, so today you receive the mail to join the session. Okay. And similarly, like you receive the link in the group or it's received from the college side. Okay. So every day you not required link as well. You can directly join the session from the LMS portal as well. Okay. Click here in live session today. There you will find the join Zoom meeting. Okay. So you can check. Clicking on this link, it will take you to the Zoom. Even you not required meeting ID or password. But if anybody is going to face a problem, then definitely you can utilize that as well. And then we have YouTube link. If you're facing the issue on Zoom, So it's streaming live on the YouTube. Our team will take care of all the queries if you're on YouTube as well. So you can join the YouTube as well. Okay. So this is how you can join the session. Then after that, a second thing, if you want to access the recording, attendance, and material, so how we can access that? So below live session pop-up, you have option of one like enroll courses. On my dashboard, it's like one to enroll courses, but for you, whatever courses you enroll with Excel as of now, let it be a free STPs or FDPs or any other program from your respective colleges, then you can check that here. Okay. So the first thing which you want to check, that is enroll course. So FDP on quantum computing. Okay. I'm clicking on that. So the first thing you will find there agenda, attendance and feedback link, class session recordings, and the material. So coming to the agenda, if you click on that, here you will find one document, and in that you will get to know that okay, so throughout this training program in this 5 days for next 10 hours, what we are going to get. So you can check the agenda. Below that, you will get the attendance and feedback. Okay. This is something again important. So dear faculty members, 60% attendance is mandatory to get the certificate of participation by Excel. Okay, so make sure that you are utilizing the one single email ID for all 5 days. Okay, and the link will be active in between 4:30 to 5:30 p.m. for 1 hour only. Okay, clear? Link will be active for 1 hour. That will be the 4:30 to 5:30. Then if you're facing any issue with the LMS for now, no need to worry. Our team will be sharing the link over the Zoom and YouTube as well at 4:30. Okay, so this is the important activity. This is one combined for attendance and feedback. So definitely you can share it, the real-time feedback with us via same form. Then below attendance and feedback, live session that I already explained how you can join the live session, session recording. Okay, so whatever 5 days recordings, it will be available here a day wise, like day 1, day 2, day 3 in a sequence, and then reading material as well, the PPT or any practice files. So that will be uploaded here over the LMS portal. Okay, so that's how we can access the LMS portal. If anybody have any doubt or any query or any question, you can just post it into the chat box. Our team will take it up. Okay. And if any further more questions, you can drop an email to us or reach out to us via edl@xlab.com. Our team will assist you on the same. Yeah. Thank you. Thank you so much, dear faculty members. And Nitya ma'am, over to you.
Thank you, Amar, for a quick walkthrough on the LMS. So now let me hand over the session to our subject matter expert, Dr. Vipul Saxena. Over to you,
Yes.
Mr. Dr.
Yes.
Vipul.
Yes. So thanks. Okay, let us begin. Let me share. 1 minute. Yes. So, yeah, welcome back to this foundation course. So, quantum, before quantum, we were having the computers, classical computers, right? So, in the classical computers, we are habitual to see do the computations, to do some rather writing a programs and following the algorithm of that, and then gradually we have developed ourselves, and we have developed a series of programming which can do a lot of complex works and complex things. So in everywhere in the industries, we are providing automation. So every industry now runs on the automation. Even in China nowadays, you may be hearing that a lot of factories are there where no worker is present, only the robots are there, right? So because it's a year of these things, so all these things are based on this algorithm, right? We are programming them, we are giving the algorithm to them, and they are working according to that. So when we have reached at this stage, so why we need this different complex complex concept which we have left in our earlier days in our class 12th days or graduation days, or we take first year engineering physics, we have only studied the physics, quantum physics. Then what is the need to bring back all these things at here? Already there is no saturation point for the classical computers. Most of the people can think like this because now they are seeing China, they are seeing Japan, they are seeing Malaysia, everywhere. We are finding the robots and they are working well with the classical algorithms, right? So now, but there is a very serious issue from the nature side, and there is a very serious issue from the hardware side. We are having the some restrictions on the hardware side where we cannot go now longer. The development is or on the upper accelerated limit. But now this acceleration is going to be end because of the limits of some hardware. Okay, so we will discuss these things in detail also. But first, let us rethink about this, that why we need the quantum computation instead of the classical computation. Okay, so rather than the computer, we will first start with the computation. Computation means when you are going to compute something, right? So let's think about this. So before the quantum, a computer, everybody knows. Yeah, but formally I have to introduce this. That computer is a programmable device. So just note down, it is a programmable device that performs the arithmetics and logical operations. And automatically, yeah, it's includes the memory, processing unit, and all that CPU and control systems, then algorithm and then the operation flow is going on. Okay. So, so now, but from the, if we will talk about from the hardware side, okay, software, it's okay. The algorithm is going on. We are giving the instructions. But that instructions is has to be passed to the machine language, right? And this compiler and all that has to be converted into the hardware language, where hardware will obey that instructions, right? So there is a bridge between them now, but we are because I think most of the faculties are from CS and IT side, so they will think on this corner. So there is a one corner on there is a software side. On the other corner, on the other corner, the gap bridge is compiler. The bridge is machine languages. Okay. On the other side, there is a hardware. Hardware. So there is no issue from the software side. So because CS and IT persons, they are looking like from the software side. No, there is no restrictions and no issue from the software side. Okay. You are having a sky as a limit. From the software side, the sky is the limit. You can go infinitely high, right? But who will bind you? You will bound it by the hardware. Because software is just not like a thing, it will run on the air, right? Yeah, sky is the limit if it is working on the air, it will be working on the air. But it is working on hardware. So whatever I'm writing something at here. So what is happening inside the loop? What is the total loop? Total loop is not completed because of the software. The total loop completed will be counted when we will include the hardware also. So this total will count the loop, this total. Okay. So this is perfectly right. This is perfectly right, this corner. But this software has to follow the instructions. Suppose you are giving some algorithm, it has to follow some instructions. So I'm withdrawing this thing something, and when I am doing this thing, then this instruction is reached through the algorithm to the software, and to the compiler is converted to the hardware side. And then what is inside the hardware? Then this hardware will decide. Suppose you are passing the instruction that follow that instruction in 2 seconds. But hardware is saying, I'm very tired. I'm heating. You may be facing a lot of problems in the heating. I'm very tired. So I cannot go less than a 5 second. So your whole algorithm will go west if hardware will deny to access, right? So there is finally, what I want to say, ultimately there is a limit from the hardware side, on which the instruction has to be followed. It is just like that in a factory. There is no limit how, suppose a startup is there or a very big investor is there. So there is no limit. Whatever amount of money something is required, he will give up to any project. But these are the persons who want to build up the product. So that is the kind of workers. So this hardware is just like the workers for us. If they will deny, they will say, no, I have a limit. We have the limits. So your whole product, your whole startup will fail. So same is the story at here. So there is ultimate limit from the hardware side. We are going to discuss it later. That fails it, okay, and that's why we need a quantum computation. That's why we need quantum computation. So what is that limit? We will start with the physics, then we will come to these limits also. So what are the fundamental things? Okay. So this is why we need the quantum. Okay. So this is the things. Now still there is a one unanswered question. You will say that yeah, you have answered this. Okay, there is no limit from the software side. There is limit from the hardware side. That is okay. But still there is one question which need to be answered. That is still we are not lacking. We have reached at this stage. The robotic is going on. So then what is the problem in the next stage? So the problem is coming at here that remove all these things. So the problem now, this is the first problem I talked about. Now the second problem is there. Yeah. Uh, let's talk about the second problem. The second problem is that when let me the second problem is that when we want to work these classical systems, classical computers, if we are working and we are withdrawing the work of these classical computers uh, to the macroscopic level. Macroscopic level means worldly level things. You can go on the millimeter size. So up to the millimeter size, meter size, okay, kilometer size, planets and all that. Okay, meter size, worldly level things, millimeter size, just inside, just lesser than the worldly level things. Okay. So if we are thinking about these on these levels, if we want to control these levels, it is very okay for the classical things. It is very much okay for the classical things, right? But the problem will occur when we want to go into depth in the lower stage. So from kilometer to meter you can go, from meter to millimeter you can go, and to the some extent from millimeter to the some extent you can go up to nanometer. Okay, so now we are at this stage that this never came in the computation. From this we have started, or there is one more bridge for the many is it's called centimeter. From this we have started, move towards the centimeter size. We have moved towards the millimeter size. Now we are moving towards the nanometer. Okay, but when we are moving towards the nanometer size, the problem will come, right? And we know that, firstly, I have discussed from the point of view of the hardware. Now, we know that hardware is made up of electronic components. Electronic components just like semiconductors. If in the beginning, if I will talk about the beginning, that was a tubes, triode valves in the tubes, right? So that was the biggie and bulky devices was used to come there in the 1950, 1960, like that. The invention of the semiconductor PN junctions and all that is was in 1950. So after that, the semiconductor things are begin to came in the electronic devices. So if we talk about the hardware side, then hardware kilometer was never there. But from the meter scale, we have started half of meter like that hardware. Then centimeter scale, we came down. We came down to millimeter scale also in the hardware side. We came down to the nanometer scale. Okay. But we were talking about that this is something different. See, what we are talking about this problem. This problem is something different from this problem. This is a different problem. This is a problem related to the first one we have discussed. Now, this is the second problem we are going to discuss, that classical computers, from the classical computers, if we want to take a work lesser than the macroscopic level, if we want to take the work of the macroscopic level, if we want to control the macroscopic components, then it is perfectly fine. Then it is perfectly fine. But the problem will come when we want to control through this classical computers, we want to control the nano level devices, or we want to control the atoms. We want to control the molecules. Then the problem will begin to come. Okay. So this is the real level problem. Okay. So I will tell you the facts that's where the original problem will come. Okay. So the classically, if we want to work on the simulation software, if we want to work, because you know that everywhere there is a computation field in computation revolution. So on this computation revolution, if you will talk about some pharma company, or if you will talk about some material science companies, they are going on the nanometer devices. So nanometer devices, so if they are coming on the nanometer devices, it means they have to simulate these nanometer devices through the classical softwares. Understand the problem? The problem is that if we want to work on the nanometer devices, nanometer level or atomic level devices, or molecular level devices, molecular level to some extent, to the 20% we can work on that from the classical. But the problem will occur when we want to work on the nanometer devices, on the atomic level devices. Atomic level devices means we want to work on the angstrom level. That angstrom level is approximately 10 to the power minus 10 meter. This nanometer level is 10 to the power minus 9 meter. This. So if we want to work on this, then a new effect will dominate. Okay, so if we want to work on this through the classical computation, then a new effect will dominate. Okay, so all these things has uh, initiated by Febner. There is a Finman scientist, physical scientist was there. So he was presenting a paper. I will come to that slide later. So then he has discussed these things. Okay, then that why we want to do these type of softwares and nanometer, atomic, and molecular simulations through this computer classic. Why we can not go for the systems which on which these systems are based. Okay, so we will come on this on the later level, but so this is the second problem. Okay, so first level problem we have answered, but now the second level problem we have to see some more slides. Then we will able to answer this question. Okay, this problem. So so the second this is the just understand that second problem, it is a very major problem. From this problem, first problem is a it's okay, it's hardware side, but the second problem is a very major problem. Okay. And the thought process has initiated from this problem. Okay. As I talked, that the subject level mastery is not sufficient. You have to be go from very root level to the modern level. Okay, on the knowledge. So because we are to some subjects, suppose we are studying this as this what subject is called as data science, right? So suppose we are studying a data science, we are studying a data management, then all these data management, data science are running from the last 10 to 15 years. It's not a new subject. Okay. So it's very easy to match up your pace according to the subject and acceleration. But at here, in the quantum, the major problem is that the books are even not written on the quantums. There are very rare books are there on the quantum. So this is the real challenge from faculty side also, that if the books are not there, then what textbook they want to be refer to the book to the students and also to themselves also. So I had been a teacher of faculty, so I know this problem. Then if there is a lack of textbook, so how you can plan your lecture? Okay, so that's another way. So the thing is that problem is that if we want to work on the nanometer devices, so we want to simulate these devices. We want to simulate these atomic and molecular devices, but simulate from which? The classical computers, right? So now there is no problem. But if we will see from the physics point of view, then there will be a problem. And this physics point of view can be observed by some of the physician, right? So any physicist can observe this dissimilarities, classical and this atomic and molecular and nanometer level. So this similarity has been observed by Feynman, and they have given the thought for this quantum machine. Okay, so let us talk about some more about classical and quantum things. So there is a some. I want to introduce some of the discrepancies between the dissimilarities between the classical and quantum. Then we will introduce this quantum machine, just described by the Feynman. So yeah, so in the classical era, the universe was a perfect machine as described by the lot of computer scientists and physicians also in the form of Turing machine. I think, I hope everybody has listened this word in the earlier courses. Turing machine. So that was the Turing machine. That was a theoretical machine which was working classically, and the concept was very fine. Based on that concept, now we have our classical computers. Okay, so this Turing machine, this Turing thesis was running all over the from the 50 years. Okay, so but that Turing machine is also based on the our classical assumptions. So what is the classical assumption? The classical assumption is that universe is a just like a perfect machine, perfect Turing machine. So during 18th and 19th century, it is believed that most of the because this origin is from physics, so we have to go to some percentage to the depth of the physics. So in the physics, in the 18th and 19th century, it is being thought that now the most of the things have been discovered. So most of the things have been discovered means in the physics they have thought about we have discovered light. They have thought about we have discovered heat. They have thought about we have discovered electricity and magnetism. Electricity. They have discovered the magnetism, and we know that all of these ruling our world nowadays. Okay, and from the 1900s, not nowadays, from the 1900s, all the fundamental concept of has begun to came up in the form of the commercial devices, the light concept, heat concept, electricity, magnetism concept. Every daily life machines are coming in the form of using these principles. light, heat, electrical, and magnetics. So it is being thought in that the all the most of the physics has been discovered. So, and also the very famous scientist Newton was there among them. Okay, for the classically. So Newton was very good contributor. 80% of the contribution to the classical physics from the Newton side, right? And Newton has also given the law of gravitation, and also given they have given gravitation, okay, and they also given a very fundamental laws in physics, that is three laws of motion. Okay, Newton's three law they have given, and then they have given, based on these three laws, they has given three equation of motion. Three equation of motion. So based on this, the Newton's three laws, three equation of motion, it was supposed to be that universe is deterministic, and it is a continuous, it is a predictable. All these three things has followed these three equation of motion, and to combination with three laws. How to follow? I will give you just a little bit of example for that. That what Newton's three laws of equation of motions? The first law governs the force, right? And the second, the equation of motions, all the three equation of motions are governing like that. P is equal to Q plus AT. Second, it is S is equal to UT plus half AT square. And the third is, everybody will think about why we want to go back at this level. If we will not go to back to this level, then we are unable to understand the origin of the quantum. Okay, so this is the root, and most of the teacher is starting this root from here. Okay, so that's why. So I just want to go beyond these things. Okay, so that's why we are introducing these things, these slides to it. So, yeah. So these are the Newton's laws of motion. What they are governing us? They are governing that u, it is the initial velocity, okay, initial velocity, and v is the final velocity, right? T is the time. Only these three are need to be remembered while understanding this equation. Okay. So what Newton's all these three equations of motions are saying that we can determine the final velocity. We can determine the final velocity if and if we can determine. Okay, we can determine if u is known. No. Okay, it's a very good example to understand that the universe is deterministic. Why the universe is deterministic? So we can know this equation predicts that we can have a v final velocity if we are having a initial velocity. After this final velocity, after a time v. So if we can have, then we can have after a 5 second also, we can have this velocity. If we are knowing this initial velocity, then we can have at the 1 hour also. We can have this velocity, we can predict. We can have this velocity at 24 hours also. We can have this velocity at 1 year also, right? And we can have this velocity at 100 years also. So now just think about that. And so the distance will be, S is the distance. So the distance will be with this analogy. If we knowing u, initial velocity, we are knowing time. Okay. Now another parameter, acceleration. Okay. Then we can have the 100-year velocity also. We can have the velocity after 1 year. We can have the velocity after 5 seconds. We can have the velocity after 1 hour. That is 60 into 60. seconds. Then into 24 hours, multiply by 24 in this equation. That means if we are having the initial velocity, only one question is given. The initial velocity is 5 meter per second. Okay, and acceleration is given. Then after any time, we can know the velocity. That means the universe is deterministic, it's continuous, and it is predictable. Okay? So, if starting condition knows, future exactly calculable, right? So, this is our classical computation, and this whole classical computers are built on this idea, right? So, our whole classical computation is already have been developed by taking this idea in behind. So, now, in the classical computers are using something like a bit, which is having a two conditions, 0 and 1. It was a very revolutionary idea at that time. Yeah, it is a revolutionary idea. There is only there is 0 means no, 1 means yes. Okay, based on these logics, yes or no, no and yes. Based on these logics, we have continuously developed our digital circuits and digital electronics and all that digital devices, and we came to develop computer finally. Okay, that is called classical computers. So the digital devices we have developed, that means the classical computers hardware for this classical computer based on semiconductor nowadays. Semiconductors, right? So, and there is a one very this point is forgotten from our mind that yeah, this observation does not disturb the reality. So, if there is a current flowing there in the classically, suppose a current is flowing, and you are measuring this current, right? It's a very much difference. So, in the quantum, this effect will be absent. See, if we are measuring this current, okay, if we are measuring this current, then if the current has a 5 ampere and we are going to measure this current, then this measurement has no effect on this value 5 ampere. Okay. So this measure we have some type of techniques that it will give a no interference in this value. Quantum says something different. Okay. Completely different. If we are going to some measurement in the quantum mechanically, then there will be a difference of values. Okay, so it will hinder the system. So this is a very big difference between the classical and computations. Okay, quantum computers. Okay, so now hmm, so we have to add this annotation. So now, some things I have described to you in the beginning that now the nature will start misbehaving when we are going at very small scale. This is not I'm saying on an airy basis. Okay, it's not on the on dreamy things. Okay, I'm saying just because our physics practicals, physics experiments, the phenomena, the which is being discovered in the physics, they are suggesting these things. Okay, so the classical laws, which is ultimately going to vanish at that very small scales, nanometer scales. Okay, and atomic scales. So when the atomic level phenomena we are going to discover, so the phenomena like black body radiation, the photoelectric effect, okay, I think everybody will know these phenomena. Okay, so the black body radiation, the photoelectric effect, atomic spectra of hydrogen atomic spectra. There are a certain dividation of white light into 7 colors. Then there is certain dividation of a one color inside the different energy levels. Okay, there is a double slit experiment which came here. They all prove that if we are going all these things have proven that when we are going to the nano level or atomic level, you can say, when we are going on atomic level, okay, then in the atomic level phenomena, these classical laws fail, vanishes. Okay, it will not work well in these levels. Okay, and 1900 is the century where I will tell you some of the history in 5 minutes. The 1900 century, a Planck scientist came. Okay, so Planck scientist came, and from this 1900, it is believed that the quantum age begins. Okay, the quantum concept or age has begun from 1900. Although it was fully explored after 1926, when Schrodinger has given some method to calculate these quantum level calculations. Then Schrodinger, then Bohr, Max Born, and this de Broglie, everyone has contributed to develop this quantum branch of the physics. Okay, so the overall summary is that because of these phenomena, there are a lot, 2 or 3 more phenomena are there. Because of that, these phenomena are purely and purely of atomic level phenomena. And when we are going to see the atomic level phenomena, the classical vanishes. Classical vanishes. So when the classical vanishes and quantum begin to dominate at the atomic level. So the main punching line is that the takeover line from this conversation is that, so when we are starting, finishing the classical limit, that is atomic level and nanometers level, the classical vanishes. Classical vanishes, quantum begins to dominate. Quantum dominates. Okay, at the atomic and nanometer level. Okay, so this is something very much important. Okay, this is something very much important. In middle of something, I will introduce some of the basic things which has originated this thing. Okay. So up to this point, we have known ourselves that that there is a hardware problem and there is a atomic level problem. Okay, while studying the classical. Now, the main problem is this, that if the problem is that there are certain impossible questions that need to be answered. The question is like this. Sorry, I was not. Okay. So why can't the classical computers simulate the atoms accurately? So I have answered this question. Because the classical physics is not equivalent to the quantum physics. Why not equivalent? In the classical physics, the nanometer level, the meter level, centimeter levels to the millimeter levels, that are sufficient. But the quantum, when we are going to the deeper level, atomic level, the quantum begin to dominate. And the laws of the quantum is something different from the classical. Then the second question is, what else if a computer followed the quantum rules instead of the classical logics? Okay, so same, this is the Feynman spark. The Feynman has pointed out at any talk in 1981, something around, he was delivering some talk. So he has pointed out, and it is in fact, this is a very, it is a very, we can say, frustration situation of the Feynman mind, that he is asking this question, that what if a computer followed the quantum rules instead of classical logic? Because Feynman is a physicist, pure physicist scientist, and he has nothing to do with the computation. But because he want to compute the atomic levels things, he want to compute the number of electrons, electronic configurations, their SPDF shells and all that, then it means he want to use the computer in this computation. So that's why he's frustrating. that when they are going to take the work from that classical computers to this level, atomic level, they are going to fail. Okay, because the calculations are so much lengthy. So after that, then this was a question answered by some Jews, that this was also some quantum mechanical scientists. So can such machines outperform the classical one? Then he said, okay, if this says okay, we will try to make it some machine based on this Feynman spark. So what the Feynman has given is a revolutionary idea. Okay, we will make this. But the one question is that can such machines outperform the classical one? Can it be dominating? So Deuce himself answered this question through his Deuce algorithm. He has designed some of the algorithm. He has designed some of the flow program to answer the complicated problems, mathematical problems. Okay. So the Deuce has answered these questions very accurately. I will say 80 to 90% accurately. So the next question, that can quantum machines solve a real world problem faster? So these things has been shown by Shores and Grover. Though the latter, I think in the today or not today, tomorrow or day after tomorrow, we will talk about some algorithms. So in that algorithm, we will try to answer these questions that the Shore and Grover has showed really real world problem can be solved by that quantum Turing machine. Okay. But he has not made, they have not made the quantum, it doesn't mean they have made the quantum machines, but they have given a theoretical idea. They have given a theoretical algorithm on the paper. That is it, yeah, it can solve. If we can make, the Deuce has answered that can machine outperform, then they have, Deuce itself tried to answer these questions in the same uh, pace. The Shore and Rowan came and they have speed up these things, and they said, yes, it can be fast, it can be, right? So they said, yes, it will be. And then after that, the most of the world level hardware scientists, they have begun to make the quantum computers. The efforts are still going on. So this is the Richard says one. The origin of the quantum computing has origin from this frustration and the thought. So there is a one conference in the MIT, the physics of computation. Okay, this is not the physics conference. It was a conference on the simulations and how to compute uh, the physical phenomena and physical elements. So that was a talk named Simulating Physics with the Computers. They has said that nature is quantum mechanical, right? The nature is quantum mechanical. I will come to this, why the nature is quantum mechanical. So the nature is quantum mechanical, and classical computers cannot efficiently simulate these systems. So which we have discussed these things, okay? So the problem was very much okay. The quantum states, this I will elaborate in the later part. The quantum states grows exponentially to the 2 power n. Everybody knows in the Boolean algebra like this. But the concept, if you talk about the qubits, to represent the 50 qubits, if I will talk about the 50 qubit, to represent the 50 qubits, 10 to the power 15, so much large numbers number of states means this number of configuration of the systems we require to represent. So there is so much large things. So there is a problem for the hardware side. Okay. So now I will come to the first problem we have discussed. So what is the fundamental limit? So what is theoretically what was the limit, and on the number side, what was the story? Okay. So the thing is like that if to begin this, just want to introduce, I want to give you one example that it's the first problem we are going to tackle here. The example is that I generally used to give this example to the academic students. Okay, so suppose there is a room, hostel room, and there are two persons in the hostel. They are living, right? So if there are two persons living in the hostel room, one room, so they can easily walk around. They can take the food, they can do the exercise, they can move their hands here and here very easily without having any limitations, right? And they can take the food. After taking food, they can walk around throughout the room. There is a plenty of space there. Okay. But what will happen? This is the first very originality. What will happen if we will increase? What will happen if we are going to increase the number of people inside the room? Sorry, I had to make a smaller room or same size. This is same size room. So what is if we want that more people will live in a room? When more people will live in a room like this, more people will live in a room. Suppose two people are there. Now, if you will introduce 10 people who want to live in this room, then what would happen? That they are not. So it's a very complicated thing. The space is getting reduced and reduced to move around their hands, right? So they are very fit to each other and they cannot move. Yeah, they can stand alone, but they cannot move their hands, do the exercise. They have to remain at a stable position. So they cannot change their position. Okay. So they has to be stable only. They cannot change their position. So now what will happen if I will go on increasing the number of people on the same size? So on the same size, now if we will say that number of peoples will be 100. So the number of peoples will be 100 now. Number of peoples are 100 now. Now it will be more typical, very much typical. They will even not, even no space will be there, so he can breathe it. Okay. If someone is breathing at here, at this position, at this position, if someone is breathing, then there is no problem. Okay. No problem in breathing. But at this position, yes, there is a problem in moving hand. Okay. There is a problem in moving hand. But at here, there is a problem when 100 people are there. Even then, there is will be problem. Okay. At here, he can breathe. At here, they can breathe. No problem in breathe. But when they are moving, they are going to move their hand. They have to disturb the other. So without disturbing any other components, he cannot move their hands. If they want to move their hands, they have to disturb the other component. Means other people, right? But at here, if even then you want to take it, this is saying if you when you want to take as a breathe, you have to disturb the other. Okay, so this is the problem. Now this problem is going worst and worst if we we are going to reduce the room space and still there will be 100 people. Then it will be very much, there will be saturation limit for ourselves. So, okay, a lot of people from very fitted size, they will here, now there will be saturation. So to some point, there will be saturation point. Okay. So now the same thing is happening with our chips, ICs. Okay. The ICs and chips transistors. Okay. We know we are running on the semiconductor ICs, integrated chips. This is called chips. And when we are running to the semiconductor chips, that means these chips having a number of components. So initially the chips are having only 10 components or 50 components or 100 components. But now the number of components are going 10 to the power 7, 10 to the power 8 components. Initially, the chip's size was centimeter, 1 centimeter into 1 centimeter. Okay. Now the size is going to on the nanometer scale. The size is going on the nanometer scale. So when we are going to the nanometer scale, see now both the problems. I told you about two problems. I told you about two problems. First problem, second problem. The first problem from the hardware side, and second problem is from going from classical to quantum side. Quantum side. Now, both the problems are coming to the same point, that is nanometer. So if we are coming to the nanometers level, then the hardware, so there is a limit from the hardware side that we cannot accommodate more than 100 now. This will resist. We cannot accommodate more people. So here it will resist, it will saturate. So 10 to the power 8 components, now you cannot accommodate more than 10 to the power 8 components in the chip. So you cannot accelerate your speed now. Okay. So there is a one problem that is coming from the hardware limitation side. This. Now the second problem is that from classical to quantum. This is the second problem, from classical to quantum. So then from classical to quantum, when we are going to the nano level size, this is the time in this year 2025, we have reached to the 26, we have reached to the nanometer size level. So we know that at the lower size, the quantum effect will begin. So when at the lower side, the quantum effect will begin. So that means both the problems will occurring because of going from the nanometer level, quantum level. Okay. Although this problem was not so much dominating in 1980, but yeah, it was a trend. Why it was a trend? Because of this Moore's law. Moore's was the founder of Intel, co-founder of Intel, right? And I will tell you, I think everybody knows about this Moore's law. That he has said that. Okay, let's be clear about this thing. So what was Moore? Moore has said that they have they have estimated the development acceleration what the companies are going to develop, and based on that development, he has not made some law. He only said that in every 2 years, he said every 2 years the number of components in the chip, number of components in the IC will be double. First, he said this. Second statement he made that, only statement he made that, and the size will become half. Okay, the number of components will become double, size will become half. So overall, the growth rate will go exponentially like that. Okay, so growth rate will go exponentially to the ICs. So now there is a limit. We have reached up to the saturation point. Okay, so that now at this point, because there is a 10 nanometer to 100 nanometer chips are being designed. Okay, we know that from Pentium series, they have started from Pentium 1, 2, 3, 4 series. We have started I series. Okay, then in the I series, there is I3, I5, and I7. Now they have launched I9. But between I7 and I9, they took a very long gap. Okay, because they know that they are at the saturation limit. And in between that, they have launched several generations. They have launched several generations. So in launching several generations, you can observe you can just follow the Wikipedia page. They will give you all of the summary of the generations and all that. So you can observe in generation wise, when they are going to increase the generation wise, they are reducing their size, chip size. And that's why, because they are reducing their chip size and they are increasing the clock frequency. So the speed is getting increasing and increasing generation wise, right? So in the i7 also, so in the i9 now, it will 10 will follow i9 also. Okay. So what is the thing? Thing is that now we have reached to the generations i3, i7, 7, 9 like that. We have reached to the limit of 10 to 1 nanometer to 100 nanometer size limit. Okay. So we have reached on this limit. So these limits are the limits at which the quantum dominates. Now, I think I have heard that the Google and IBM, so means both are Intel and IBM both are planning to launch 1 to 3 nanometer limit chip. It's very typical, very typical to launch this chip size. So now, within a coming 2 3 years, they are going to launch this 1 to 3 nanometer chip. Okay. So I think before 3 or 4 months, we had a meeting. Then in that, I have listened this treatment from them. So they are going to launch this. So now, if they will launch this 1 to 3 nanometer chip, then it will be a ultimate saturation point of the classical. Okay, it will be a ultimate saturation point from the classical point of view. So when a limit will be reached there, then we have to search for another option. Okay, so all these things are from hardware side limitations. So we have to look up for the mm, we have to look up for this computation, quantum computation. Hmm. One minute. So the thought was initiated by Feynman. So why we want to originate? We want to originate because Feynman was trying to take a work of atomic level or nano level simulation work or computation work from the classical computers, and they are not able to find the good result. Okay, they are not able to find that classical computers are uh, not able to even take the inputs from the atomic computers, because we know at the atomic level there is a so much less level. That means the number of input will be very high. Okay, so the classical computers are not able to take that inputs even. Okay, so that's why in the frustration they said that, and in 1981 he was a physicist, so they know that the nature supports the quantum. Why the nature supports the quantum? Because of these things. Okay, so the nature starts misbehaving when they are going on the quantum. So they know the fact that the nature supports the black body radiation, photodynamic effect, all these phenomena. We know that we have developed the quantum mechanics. So that means this was the idea inside the Feynman mind, that when we have developed the quantum mechanics, then why we are working on the classical computers, which is based on the classical computers. Okay, so that was the punchline. So Feynman was saying that why we are working with these classical computers. This is in fact the frustration only, frustration of Feynman, that why we are working with the classical computers when nature has allowed us to compute quantum mechanically. When nature is computing classical quantum mechanically because of these things, black body radiation, Feynman has said that, Feynman has observed that black body radiation have observed the photoelectric effect, atomic spectra, and all these. So it's saying that nature is allowing us to go on the quantum, then why we are not going on the quantum? So that was the spark point from the to initiate the quantum computing. Okay. So now come that we have seen that classical limit uh, of the uh, old hardwares, okay, semiconductor size, okay. Now, what happens? What is different from the so your mind will certainly ask that we are talking so much about the classical as very much rough level. Classical, we don't want to use that, but still there was a lot of robotics advancing as there. Okay, industries they are going on the automation. So when every industry is going on the automation, we are getting a faster products. Then why? The thing is this hardware limit and all that quantum nature. So, but now, what is the difference between the quantum, classical, you are talking about physics. So there are a lot of differences between the classical and computation and quantum computation. Okay. So to start the difference, I will give you a 5 minute story. Sorry, I have to go somewhere because it is the starting day. So I don't want to start like a content like things. Okay. So I don't want to give you because it's a faculty development program. It's not uh, students are there. The faculties are with me. So I have to go from the very room. Very, because I know there is a very much problems from the faculties because the faculties are from the computer background. Okay, so why they will go into the background of the physics? So there is no need, right? So it's a very typical. So we cannot overburden the faculties. We cannot can say the faculties. You just go to the mathematics. You just go to the core hardcore physics. Okay. So with this approach, I designed these things to go in this level. And generally the MDPs, I'm just telling all these books because it's very, it's not an impossible task, but it's a very difficult task to, along with your hardcore subject, core subject is this class, this computation. So along with your core subjects, you have to go a lot of languages and all that classes you have to learn. So it's very typical to find time for this hardcore physics. That's fine. Okay. So with this approach, I want to give you some 5 minute description of the what is the difference between classical and quantum. So we have to go for the classical physics and quantum physics difference. So not so much detail I want to go. I just start historically and will uh, uh, move with the timeline, right? So that you can only know what is the surface level things are going on from classical to computer shift, quantum shift. Okay. So let me give you the one. So let's I will share some whiteboard. Okay. One minute. Hmm. So I will start somewhere from the Newton's era. Okay. So actually, this whole thing from shift from classical to computer, classical to quantum, is this whole shift, quantum shift. This shift is coming from the fact, please do not run, the participant, please, I request you do not run something else on the whiteboard. Yeah. So, okay, I have to, 1 minute. Hmm. Yes. Hmm. So, from classical to quantum shift, so it starts from the Newton that in 1597 or 1595 around, these all dates I will tell you approximate dates, just for the sake of your exact date, just go to refer to the any uh, internet material. Okay. So in around 1595, the Newton has come up with its corpuscles theory. Corpuscles theory. The whole thing, this shift has originated by starting the question that what is the nature of the light? Okay, what is the nature of the light? So, in the quest of searching the nature of the light, Newton has given corpuscles theory, and so Newton has given some corpuscles theory, and they said of that light is consist of these corpuscles. This corpuscle. I will write something about corpuscles. Okay. So light is composed of corpuscles. Corpuscles are nothing but tiny particles. Tiny particles. Okay. So they said that the light is composed of tiny particles, right? But after certain years, there was a Huygens. Okay. If you know the class 12th physics, then I think you may be reminding all these things. Then Huygens came, that is in the 1630. The Huygens came, Huygens said that the light is not a particle. Light is wave. It is a some sort of wave. Okay. Then, but it was not considered as a wave because Newton was very greatest scientist of that era. Okay. So Huygens came and has given his theory, but it was under dominated stage, and the Newtons has dominated over the Huygens. But when after 200 years, in 1830 or 40 around, Young's double slit experiment come. Young's double slit experiment. Double slit experiment came, and Young said that actually the double slit experiment he first did with the sound waves. He first did with the sound waves, and he observed that there is certain increase and decrease in sounds. Okay. So the same pattern when he did same experiment with the light, same experiment with the light, he observed the same pattern. He observed same pattern. Okay. So he has concluded that the light is somewhat behaving like a wave. So that's why he declared that yeah, Huygens was right. So Huygens theory was proved to be existing in this here. So from that, the light is considered as a wave, and we know light is a wave. Okay, but the twist will come now. So why I am describing this theory, it has the direct correlation with the quantum nature. Okay. So when there is a wave, light is now proven as a wave, but in 1900 something, 1819 to 1905, there was something which I was talking about, some black body radiation, some atomic radiations, atomic spectra, and all that. So that had showed that light is all these phenomena are not explained by wave. Okay, all these phenomena was not explained by the wave nature. Then in 1900, then in 1900, one minute. Hmm. Hmm. Then in 1900, one minute. Hmm. In 1900, Planck came, and Planck said that light is consist of photons. Photon is again a particle. Photon is again a particle. So when photon is again a particle, so that means, but it was a hypothesis in 1900. But when Einstein has proven for the photoelectric effect in 1905, okay, he has utilized this photonic nature to explain the photoelectric effect. Photoelectric effect. Then it has been proved. So the twist was that previously it was a particle, corpuscles or tiny particle. After that, it has proven to be a wave. Then again, it has proven in 1900, it has proven to be a wave from 1600 to 1800, right? In 1500 something, 1597, it was a particle. In 1618, it was a wave. Then in 1900, again, it is turned to be particle. Okay? Again, it is turns to be particle. Now, the whole scientific community was divided in two parts. That what the light is. Light is a particle or a wave. Particle or a wave. So when the light is particle or a wave, to answer this question, de Broglie came. To answer this question, de Broglie came. It's a timeline history, nothing else, okay? De Broglie came, and de Broglie said that it has both particle nature as well as the wave nature. And here the starting of the quantum begins. When somebody is saying that particle is a wave, okay? Something is saying that particle is a wave. So that means there must be some particle properties which is equivalent to the wave property. So the particle properties are that mass and velocity. Fine. The wave velocity, the wave properties are that wavelength. Fine. So there has to be some relation. So they have given some relation, that is lambda is equal to h over mv. There is a relation between particle and wave properties. Okay. H is working as a bridge between the wave nature and particle nature. Okay. So this is like a wave and particle nature. Okay. So now, but then after that, after the de Broglie, Schrodinger has given that if it is a wave, then we have to deal with the wave equation. Then Schrodinger has given some wave equation. Okay. Schrodinger has given some wave equation. So we were reading in BTech first year and graduation hour. Okay, there's Schrodinger equations. Okay, so maybe in some part of the chemistry of class 12th. Okay, Schrodinger has given the wave equation, and from that wave equation, we have deduced a letter psi. And from this psi, we will start our quantum computation. Okay, the principle of the quantum, the postulate of the quantum computation. Okay, so that is a so much large historical development. Again, I'm repeating. 1 minute. The Newton was there in 1595. Okay, you just note down approximate date, then you can search on the net. Okay, then they have given a corpuscle theory, tiny particles. Then Huygens came 1630. Then he had given a wave theory, but it was not proven. But 1830 Young's double slit reaction was there, and he has proved the Huygens wave theory. So the wave theory was established, and after 70 to 80 years, then there was a problem coming in the physics experiment also, physics phenomena also. There are some phenomena, globular radiation, photoelectric effect. There are some spectra that they are not able to explain with the wave theory. They are not able to explain with the wave theory. Then in 1900, Planck came with this hypothesis photon. The light is consist of a bundle of photons. That means he has again moved to the particles. Okay. So then the end of this fight has been by de Broglie. De Broglie said that light is a particle as well as a wave. And when light is a particle and wave, it means this fact is established that every particle can have a wave-like behavior. So when they has a wave-like behavior, then Schrodinger gave us the wave equation. That is called Schrodinger wave equation. And from that, the Schrodinger wave equation, we have received this magical letter psi. This is called psi. And based on this psi magical letter, the whole quantum computation are based on. Okay? The whole quantum computation are based on. Okay. Now I will talk about subdiscreteness. See, because it was the struggle between particle and wave. Particle and wave nature. So we have to see, so what predict the particle nature, what wave nature predict us. Okay. So the particle that predicts us are discreteness. And wave nature predicts us a continuity. And this is the whole idea of the quantum computation. Okay. Because discreteness, see there, suppose if some particle is there, this is some particle, the small particle is there, and if this particle has to move here and here and here and here, right? Then this particle has to jump from this to this, A to B to C, like this. Okay. You will say that no, you have made a distance larger. That's why it has to jump. If you will make a distance closer, okay, just make the distance very closer. This is the particle. Make the distance very closer. Okay. What? How much close? Okay. If particle has to be round shape, then if you will close it, has to be like this. Okay. So that means how much, whatever you place the particle, okay, ahead of this, it has to be jump up to skip some position. So what mean to say, there should be some discontinuity. there should be some discontinuity. However, this discontinuity level is so much low, but it will be. Okay, it will be having a discontinuity in traveling. So the particle itself shows a discreteness behavior in itself. Okay, but however, wave is a continuous thing. Wave is a continuous thing. Okay, so always understand from the student point of view, if I say that if you want to deal with the students, then you can say to the students that the particles are discreteness. Discreteness is governed by the mathematical operator like this. When you want to add up, because we want to add up from this to this, all these things. So if you want to add up the particle motion, you can go on the summation, right? So, and for the wave continuity, for the wave, if you want to mathematical operation, you can give on the integration. There is the basic difference between the summation and the integration. If you want to add up discrete things, you can go on this. If you want to add up the continuous thing, you can go on this thing. Okay. So there is a difference between discreteness and continuity, that is particle and wave nature. And from this discreteness, there is a story now we are going to read it in our code is discreteness to continuity. Particle nature from wave nature. And this discreteness, this is the discreteness property that gives us that discontinuity. That is, at some point it will be 0, at other point it will be 1. There is a discreteness, 0 to 1, direct jump. However, if we are not going on the direct jump, if from 0, we have to move, then another state is 0.0001, another state 0.0002, another state 0.0003, then another state 0.0009, after that another state 0.09, like that. Okay, then there will be a continuous thing, right? So instead of jumping directly from 0 to 1, we have to include all these things in between the way. That is called continuity, and this is called quantum. Okay, so we have to include not going to 0 to 1 directly. We have to include all the things from 0 to 1 in the way going from 0 to 1. And so how to include all the things running from 0 to 1? That means at every point there will be a different stages. There is only 2 stages at this and this. If we want to make it continuous from this to this, so at every point of this path will work as a source to store some information. Okay, and that is how this is called. This concept we have innovated the qubit. This concept we have innovated in the bit, but this concept we have incubated in the qubit definition. So what the definition of qubit is, bit's value is either 0 or 1. The qubit value is either 0 or 1 or between 0 and 1 is mix of 0 and 1. This is okay. So based on this, we have transit from bit to qubit. Okay. So there is a very genuine shift from classical to quantum, or we can say discreteness to continuity. We can say from summation to integration. Okay. So this shift we have to go along with these things. This is the starting point. So all we have discussed about the quantum, how this quantum has begun, what was the initial spark, initial level of phenomenon to begin this quantum, okay, with what thought. So it is just like a thing in the end. We want to say that it is just like if suppose if I will talk about India, it's just like a building a new city, a quantum city. Okay. So just like I will give you, so most of the times I'm giving us examples of this Chandigarh, which is in Punjab. That's the capital of Punjab, Haryana. Chandigarh is a type of planned city. It's not built up randomly. So all of the cities you are seeing now, there is no provision to flood it water. There is no provision where the garbage will go or not. There is no provision what one way to connect it to another way. So making a provision after development. But in the Chandigarh, you just see there is a planned city. The architecture has been planned very first initially on the first point, right? So this quantum we are developing nowadays. That means it's a plant. It's like a plant city. So everything we are developing with our planning. Okay. So from this shift, how we are shifting this to this, what are the mathematical tools we are going to use it here, we will discuss later on the second session. Okay. So that's it from my side. And if there is any on the end, if there is any questions, any queries, you can text on the chat itself. So if there any query thing to say, then you can chat. So okay. So okay, that's it. So hand it over to Nitya if there is.
Yeah, yes, sir. Sushmita here. Thank you so much
Yes, yes.
for day one session. We'll meet again by tomorrow at 3 p.m. So thank you.
Okay, thanks.
Yeah, so dear faculty members, the attendance link has been shared on a chat. I request please mark your attendance. As we inform, the attendance link will be active only till 5:30. So before that, you all should mark the attendance. And there is one more important announcement. This is a faculty development program. So only for faculties will get the certificate. The student won't get the certificate as they can join for their knowledge purpose, but they will not get, if they have marked the attendance also, the students won't get the certificate of faculty development program. So yeah, as I told, they can join for the knowledge purpose. And the 60% of attendance is very mandatory to get the certificate. So I request please join the session every day and mark your attendance and get the certificate. So as if you have not secured 60% or above 60% of attendance, you will not get the certificate. And the session link, so every day the session link will be the same. Whatever which you have used to join today, the Zoom link will be the same, but the YouTube link will be different. So as we have showed you how to join the classes from LMS as well, you can join through LMS as well, and you can use the same Zoom link for tomorrow's sessions as well. So I request please join on time at 3 p.m. Every day, all the 5 days is till Friday. So by using the same Zoom link, or you can go join from LMS as well. Okay. I think we can just wind up for the day. So yeah, thank you all. Thank you for joining. Have a great day.